Hello and welcome back to the Math and Physics podcast. I am your host, Parker.
And I am Ray, and we welcome you back to episode 8. And today we're going to be talking about special relativity. So let's kick it off, Parker.
Yeah, that's right. So before we actually start talking about special relativity, we're going to talk about Galilean relativity. So Galilean relativity is just the study of speeds, right? Or positions and velocities based on different frames. Or in this case, we're only talking about inertial frames, right?
Mm-hmm. Yeah, and the big thing with Galilean relativity is that it measures the velocity relativistically. Like, for example, it's actually very, very straightforward. It's like if there's one bike going in one direction at 5 kilometers an hour, and there's another bike going in opposite direction at 5 kilometers an hour, each will view each other at 10 kilometers an hour just by adding up the speeds because they're going in opposite directions. So that's pretty much the gist of Galilean relativity. Very, very straightforward. However, the big thing about Galilean relativity is that it assumes that the time interval for each observer is the same. Now that's the big difference between Galilean and special relativity, and we're going to talk more about it. Yeah.
Because this comes up this was in like the 1600s, right? I'm pretty sure.
Galilean? Yeah, I think so.
Yeah, he really had no idea about, special relativity and all that, obviously, because this came up before special relativity. And so all of these cases kind of have to do with simple things that we can see on Earth, right? So if I'm running at 10 meters per second and someone is also running at 10 meters per second beside me, it's going to seem like none of us are moving relative to each other. But relative to the ground, we're both going to be moving at 10 meters per second. But, things start to get a little different once you start reaching velocities close to the speed of light. And that's what we'll get into later.
Yeah, and the speed of light, also interesting fact, was also not known in the 1600s, and therefore Galilean relativity technically did not even include what would happen if you are close to the speed of light. So technically, if we use the Galilean equations, if, let's say, we are moving, beside a photon, I don't know if that's possible, but let's say we're moving beside a photon, Galilean relativity states that the photon would be moving at speed 0. But special relativity and real life experiments tell us whichever frame we are in, the speed of light will always be equal to the speed of light. And that is something that we can only measure using special relativity. But Galilean relativity just completely does not account for the fact that there is a maximum universal speed.
Yeah, so like I said before, Galilean relativity is primarily used for like easy situations that we can observe here on Earth, most of the time. But, as soon as you start, or you discover, I guess, that the speed of light is the speed limit of the universe, you kind of ask yourself, well, if I accelerate, this has nothing to do with relativity because we're talking about acceleration. But let's say I accelerate at a constant rate for a very long time, eventually will I just, reach the speed of light and, cross that threshold and just keep accelerating? Well, the answer is obviously no. And we're going to talk about the implications of that and how like time and space can kind of shift based on your frame of reference relative to another.
Now, one big disclosure that we should probably say, we kind of implicitly said it, but we should explicitly say it to the entire audience that when we're talking about special relativity, just like Parker gave the example of acceleration, just a quick note, special relativity does not include acceleration and only includes inertial reference frames, which means the frame that we are in is non-accelerating. That means that we can go at constant velocity, zero velocity, negative velocity, doesn't matter, but no acceleration. However, there is an equation to have relativity or to solve for the relativistic effects when a frame is accelerating, and that is covered in general relativity, which took Einstein 10 years to come up with. So we're not going to be trying and summing it up in 30 minutes. So today we're just going to be talking about special relativity, and once again, focusing on the non-accelerating frames.
Yeah, and it's also much more complicated than
Oh, so
special
much more.
relativity.
Yeah.
And we haven't even learned it yet. So, eventually we will have an episode on general relativity when we get there.
General relativity is actually a master's level course, so the episode will
Yeah.
probably come in 4 to 5 years, to be honest.
Yeah. So I just wanted to say, if somebody in the audience doesn't know what an inertial frame is, here's a way to imagine it. Okay. So let's say you're floating in space and you can't see anything around you. There's just, darkness everywhere. Your body is in an inertial frame because you feel like you are at rest. Now, imagine Rayhan comes along and he's zooming past you. Okay. 30 seconds ago, I couldn't see Rayhan and Rayhan couldn't see me. So in his head, he was just at rest and I was zooming past him. But in my head, I was at rest and he was zooming past me. So we were both in inertial frames of reference because we can't really know who was actually at rest or if both of us were in motion, right? If we're not accelerating, then there's no way to know which one is at rest, and that's why we use the term inertial reference frame, because no one is in the right. I'm not the one, or I might not be the one that's moving and he is, or maybe he's at rest, or that's just what we call an inertial frame. When you're moving at a constant velocity or you're at rest, you have your own inertial frame.
And a really important thing, at least a very, very important thing about relativity is, well, it's in the word relative, right? So whenever we're talking about, oh, I'm going at 5 meters per second, or my car is traveling at 60 kilometers an hour, even though that's a widely accepted statement, we have to say with respect to the ground, or with respect to an observer who is outside of the car. Because, for example, if our car, as Parker just said, if our car, let's say, is going at 60 kilometers an hour and I am driving the car, then I will be moving at 0 meters per second with respect to the car. But I will be moving at 60 kilometers an hour with respect to the ground or any outside observer that is stationary relative to the ground. And that's why relativity is so important, is because your speed, your time, everything depends on who or what you are comparing it with. And that comparison is really that determines what your speed is and what your time interval is and all those different parameters.
Yeah, when you're attacking like a problem with relativity, it's super, super important to always know which frame you're in, because the question could be asked in such a way so that the frame of the Earth doesn't even matter, right? You're just concerned with, let's say, a car and a bike that are moving at different speeds in different directions. You just need to know which frame you're dealing with and which speeds, or I guess which velocities you're using in which frame.
Mm-hmm. So now we can talk about the two postulates for special relativity, or Einstein's two postulates. So as we know, special relativity was published in 1905, and general was published, I believe, in 1916. And as I said, right now we're just going to be talking about special. So I'll start with the first postulate, and Parker can move on to the second. So the first postulate is simply the relativity postulate, which states the laws of physics are the same for all observers in all inertial reference frames. What that means is, whatever inertial reference frame you're in, that means if you're moving at 5 meters per second or 5,000 meters per second, whatever reference frame, remember inertial, that you are in, the laws of physics, that means the kinematics, the dynamics of your motion, all the different fields that you are currently in, the laws will never change. The laws of physics will always be the same no matter what reference frame you are referring to. And that's the first postulate of special relativity.
Yeah, the second one is the speed of light postulate, and it states that the speed of light has the same value in all directions and in all inertial reference frames. So we talked about that before. The speed of light is the same, whether I don't think we talked about the speed of light while
We didn't talk about it too much. No.
yeah, but so the speed of light is the same everywhere in the universe, supposedly. That's the postulate. And even if I'm moving, 1,000 kilometers per hour in one direction, if I'm holding a light bulb in front of me, then the light will be emitted at the speed of light, in
Hmm.
front of me or in all directions, I guess. But if someone is standing next to me as I pass by them, the light will still be moving at the speed of light. And that might seem really obvious, but, you know, some people might expect that if I'm moving at 1,000 kilometers per hour and I turn on a light in front of me, I will see the light moving at the speed of light minus a thousand
Hmm.
kilometers per hour. But that's not how it
That's
works
not true.
because, yeah,
Hmm.
the postulate states that it's the same speed in all inertial reference frames.
And I actually think that is one of the biggest hurdles to get over when you're just starting to understand special relativity,
Yeah, me too.
because it doesn't really make that much sense, right? Because as we were talking about just general relativity questions, like I'm moving at 10, my friend's moving at 8, what's the relativistic speed? Oh, my friend is moving at 2 meters per second faster than I am. But when we're talking about light, it doesn't work that way, just like Parker outlined. And that's why I think the big hurdle that everyone has to cross when really truly understanding special relativity is that the speed of light is constant. Even though we keep saying it to ourselves, it doesn't really conceptually come into our head because we're so used to the Galilean relativity that we can't really picture the speed of light being constant in any frame. And that's why it's interesting, because even if a particle, let's say a proton, okay, protons can't move that fast. Let's say, I don't know, maybe a muon, for example, moving at 98% the speed of light. Now, if a muon is moving at 98 or 99% the speed of light, it wouldn't make sense that in the muon's frame, the photon travels at the speed of light, but it does. And this, again, is the big misunderstanding or non visualization problem when it comes to understanding special relativity.
Yeah, so knowing that the speed of light is constant in all inertial frames, we can get into I think, the most famous thought experiment that is used to demonstrate time dilation. Okay,
Mm-hmm.
so let me set this one up. So you're holding two mirrors in front of you that are, vertical and parallel to each other. And in your frame of reference, you are at rest, but in someone else's frame of reference that is standing, next to you on the earth, let's say, you are moving very quickly. Let's say 1,000 kilometers per hour. Why not? And
Mm-hmm.
so at that point, um, or not at that point, but at any point, you emit a photon that bounces from the bottom mirror to the top mirror and then back down. Okay, so in your frame of reference, the photon is moving at the speed of light. It just goes straight up at the speed of light, bounces back straight down at the speed of light, and it will take a certain amount of time. But because the speed of light moves, actually, I'm going to get to this after, but so your friend who's watching you, because he sees the two mirrors moving, the photon starts at the bottom mirror and goes towards the top mirror. But because both mirrors are moving, it has a diagonal path. And so once it reaches the top mirror, the mirrors are still moving and it bounces back and has another diagonal path down to the bottom mirror. Here's the thing: the amount of time it takes to for the photon to go up and down in your frame should be less than, or no, yeah, it should be less than it takes for the photon to move, in the diagonal path,
Mm-hmm.
because it's a diagonal path, it's automatically longer than the straightforward path that just goes up and down. And because the speed of light moves at the same rate, you get a little bit of, you get some complications based on, how much time does it actually take for it to go up and down. Should it be the same, right? Who knows? Well, turns out some people know, such as me and Ray. And you can get into, like, you can draw the whole experiment out and annotate it with like the heights and the times and stuff like that. And the answer that you'll find is that it turns out that the frame in which the person is moving takes less time than the person that is at rest, which means that, let's say, this kind of implies this next scenario. If two twins were born on the same day, obviously, and one of them were to be sent out on a rocket ship at very close to the speed of light, and then come back 60 Earth years later, the two twins would now be different ages. The one that was sent out on the rocket would be younger than the one that stayed on Earth.
And that's simply because of the awesome effect known as time dilation. So I think Parker explained it to the best of his ability when it comes to explaining a thought experiment in a podcast, because I don't really
Yeah.
think there's much we can do without like a video or us representing it to you. So if anyone is listening to this, I do recommend maybe watching a video on the thought experiment of time dilation, because there's only so much we can do on an audio file to explain it, right?
Yeah, Brian Cox has a really good,
Oh, Brian Cox is a genius. I love that guy's show. Yeah.
he has a video on YouTube where he kind of demonstrates the light bouncing experiment, and he does it like in front of a crowd, and it's
Mhm.
really interesting, really cool. He explains it super well. So definitely go search that on YouTube.
So another thing when it comes to special relativity, so now we've gone through time dilation. Now another major aspect of special relativity is known as length contraction. So length contraction is actually kind of, as said in the name, dilate versus contract. It's kind of the opposite of time dilation. So where time dilation in the frame which is moving, the time slows down. In length contraction, the frame that is moving, the length or the perceived relativistic length is supposedly larger or longer. So it's kind of the opposite of time dilation. Now, once again, it's hard to explain it without use of formulas and imagery to really explain length contraction, but I'll do the best that I can in a way where, think of a train moving on a platform. Now, the train can either be the length of the platform, longer than the length of the platform, or shorter. So the person that is observing the train that is moving will either be able to tell longer, shorter, or exactly equal to the length of the platform. However, the person that is on the train will not be able to tell the same thing. Why? Because the train is in motion. Because the train is in motion, the person that is on the train will view the platform a lot shorter than the person that is outside of the train. And that is why length contraction is so important, is because it kind of tells us, relativistically speaking, who or in which frame are we measuring the length and how it differs. So the reason this is important is because, for example, if we were traveling really, really close to the speed of light, let's say 98% or 99% of the speed of light, and I'm going to give you a concrete example later on, but for now, let's just go through the analogies. So let's say we're going at 99% the speed of light. Now, the interesting thing about moving really fast, and moving really fast relative to the speed of light, is the fact that length contraction and time dilation will come into the picture. So we've already kind of explained time dilation, that if we move 98% the speed of light, our time will very much slow down. But then what will happen to what we perceive outside of, let's say, the spaceship that we are in? So if we are in the spaceship moving at 98% of the speed of light, what we see outside is pretty much nothing. Because we're moving so close to the speed of light, everything that we see has now been contracted to the highest possible amount. That means if, let's say, something was originally 1 meter long and was stationary relative to our spaceship, I would now maybe view it at 0.001 meters long, because I'm traveling so fast. And here's where the interesting thing comes in. Hypothetically, let's say we can travel at the speed of light, we would see literally nothing, because time would be completely stopped and length wouldn't exist. So if we were to move at the speed of light, which is impossible, but let's say we are, it would be such that we would not be able to tell where we are, what we are doing, or when we are, because the entire concept of when and where will be lost, because there's no concept of time or length when you're traveling at the speed of light. And the closer you get to the speed of light, the more these factors, these dilated times and these shortened out lengths, the more they actually matter. So I know I was talking a lot, but yeah, Parker, continue.
Yeah, I just realized like this is gonna be really hard to understand
I
if you
know, I
don't
know.
if you don't already know a little bit about special relativity. It's all in the math, to be honest. Like if you see, or if you attend a physics class and you see it step by step
Hmm.
why time dilates and why length contracts, and you do the thought experiments in class. You don't do the same thought experiments, you don't do the whole train thing, but we work with inertial frames and we see like what's it called, like animations of like light pulses and stuff like that. It becomes a
Hmm.
little bit more intuitive.
Yeah, that's exactly why explaining it on the podcast is a little hard of a
Yeah,
job to do. But as I said, I mean, we're trying our best. But if you don't already know at least a little bit about special relativity, this podcast might be a little hard to understand.
yeah. Did you want to talk about muon decay?
Yeah, of course. Okay, so now, as I was saying, I'm going to come to an actual example. So let's talk about the actual example. So I'm going to be talking about a muon that is hypothetically coming into our atmosphere. So a muon is a particle part of a cosmic ray. So a kind of a cosmic ray particle, and the muon is what carries that force. So let's say, or not really carries that force, but the muon is part of a cosmic ray. It's a particle part of cosmic rays. So let's say this muon is now coming towards the Earth at, let's say, 98 or 99% the speed of light. Now, the interesting thing about, once again, going so fast is that time and length, distance are all completely warped. So, let's say the atmosphere is 100 kilometers above. Let's say the muon hits it at 100 kilometers above. I'm just giving an example, not exact, but let's say. So, if it's 100 kilometers above, because the muon is moving so fast, I'm not going to give exact numbers because I haven't done the calculation. I'll just give hypothetical numbers. But instead of traveling 100 kilometers, the muon will say, let's say, travel 5 kilometers. It's a lot less. And the main reason is because the muon is moving so fast relative to the speed of light that distance is warped. So the original 100 kilometers, it'll still be 100 kilometers. A person from Earth will still view the muon moving downwards moving downwards for 100 kilometers. However, if, let's say, somehow we got a jet to sit on the muon, not possible, but let's say we did, we were sitting on the muon, we would not measure 100 kilometers. Instead, we would measure about 5 kilometers. And another interesting thing about muon decay is muons in real life, if you just let them be stationary, will die in a very, or decay, I should say, in a very, very short interval of time. But because these muons from cosmic rays are moving at 98 and 99% the speed of light, time gets dilated. So the muon in the muon's frame of reference will live the same amount. But in the Earth's frame of reference, now this is where it gets important. In the Earth's frame of reference, that means if you are an observer on Earth, you will observe that the muon takes a lot longer to decay when it's traveling at a 99% the speed of light, rather than when it is traveling at 0 meters per second. And this is because of time dilation. So muons will reach the bottom of the Earth, or a muon detector, for the only reason that they are traveling so close to the speed of light. And time is dilated and length is contracted. And only because of how special relativity and how all of these numbers pretty much interact with each other, because of that, we are able to detect a muon. If it wasn't for relativity, muon detection would be impossible, because the second that they hit our atmosphere, they would already decay. But because of special relativity and time dilation and how time gets slowed down when you are traveling close to the speed of light. The only reason we can detect the muon is because of this slowed down relativity. And that's pretty much a gist of muon decay. A little extra gist, but a little bit.
You explained that pretty well, I think.
Thank you.
This, if you don't know what a muon is, you know, we say this a lot, but it's easier to know if you already know, I guess.
I guess,
Um,
yeah.
so one thing I wanted to talk about is the famous equation that is E equals mc squared. And it
Oh.
turns out that, well, so E is energy, m is mass, and c squared is the speed of light squared. And, it works a lot of the time, but we're kind of lying to you, right? And we just realized this this year, that E equals mc squared should actually be written as E equals gamma mc squared. And gamma is the Lorentz factor, that is 1 divided by the square root of 1 minus the speed that you're moving at squared divided by the speed of light squared. And so this is the factor by which, time dilates and lengths contract,
Mm-hmm.
based on how fast you're moving. And you can just plug this in to the respective equations, and then you'll get answers based off of that. And it also turns out that E equals mc squared is, or should be written as E equals gamma mc squared. The thing about gamma is that when you're moving at very slow speeds, because
Mm-hmm.
c is such a big number, if you're moving at a very slow speed, the gamma factor will basically be just 1. And so it won't change, your time, your
Yeah.
length, or your energy, right?
Yeah.
But as soon as you reach quite a significant velocity, that's when the gamma factor actually makes a difference. And so usually we don't include gamma in the famous equation, but it should actually be written with the Lorentz factor.
Well, if we are talking about a technicality, well, then technically E equals mc squared itself is sort of wrong because the actual equation is E squared equals pc whole squared plus mc squared whole squared, right? Because that's the original equation brought from Pythagorean theorem.
Yeah, p being the momentum.
And when we're talking about light and other sorts of particles, we usually tend to simply drop it because we assume that the momentum, we're not talking about momentum and we're simply trying to find the energy relating to whatever mass this thing has. But the reason E equals mc squared doesn't necessarily work is because, take light for example. Light has a mass of 0. So technically, does that mean that light has 0 energy? Well,
Yeah.
obviously not, right? Because light has momentum, light has energy. It's just that E equals mc squared is a much run down version of the actual formula, which I just said is that huge Pythagorean theorem one. And if we apply that to light or photons, then we can accurately calculate the energy relating to photons. And that's why knowing that E equals mc squared is not necessarily the formula that Einstein wrote in his papers is quite important.
Yeah. So I wanted to talk about relativistic velocities, but I don't think we have time for that right now.
Oh, it's already 30 minutes.
Yeah. So I'm down to do another episode later about special relativity where we get
Oh,
into,
of
you know,
course.
different things and
Mm-hmm.
maybe a little bit deeper into the math and the physics behind it if, people are ready for that.
Mm-hmm. I just want to say one thing, though, if you don't mind, talking about space time intervals. Do we still have maybe like a minute to talk about it?
Yeah, sure.
Okay, so I'm just gonna run this down quick and hopefully explain it well. So as we were explaining, because of length contraction and time dilation, right? The space interval, that means the amount of distance that was passed, for example, in the muon decay problem, will not be the same and it will change from observer to observer. For example, on the muon versus on the Earth observing the muon. The length that will be measured by each party will be different, and therefore the space interval will not be the same. And I was also talking about, in the same, let's say, analogy, talking about muon decay, we're talking about time dilation. The time interval will also not be the same between these two events, between the muon hitting the atmosphere and then hitting the muon detector. The interval measured by the muon and the interval measured by a human or an observer on the Earth will be different. However, here's where space-time comes in. And I think we can give a little bit of suspense so we can talk about space-time intervals in the next podcast. But the space-time interval, that means the interval that is elapsed, or the time, not necessarily the time, sorry, let me rephrase, the space-time that is elapsed between these two events, the muon hitting the atmosphere and then hitting the muon detector, that will not change and is invariant to all reference frames, meaning that the space-time interval between these two events will be the same for the muon, the observer on Earth, the Milky Way, the solar system, whatever.
Just everything.
Pretty much everything, because space-time intervals are invariant, meaning they do not change relative to the reference frame. So yeah, so anyways, I just thought that that would be pretty important, because we have to understand that even though space can't be invariant, time can't be invariant, space-time still can be invariant. And that's pretty much what I wanted just to end with. And I think we've pretty much already gone past our date, our
All right.
time limit. So
Okay, awesome. So this has been the 8th episode of the Math and Physics podcast. I hope you enjoyed, and tune in next time. We have, I
absolutely.
think, an interview is going to be our next episode.
Oh, that sounds fun. Who
Yeah.
is it? Well, wait to find out.
All right. So this has been Parker.
And I am Ray, and we will see you soon.
See ya.